Very good afternoon, everyone. This is our last interaction where we are going to discuss everything that we have learned from the week 1 to week 12 throughout the course. So, whatever doubt you have, whatever problem which you are facing when going through this particular week in this particular course, we can interact that and we can solve the questions based on them. We can have a one-on-one discussion. So if you feel any doubt if you are having, you can always put it in the comment box. You can put it in the text and also the discussion forum. There will definitely try to respond to them. So in this particular session, what we are going to do, we'll solve few questions based on the assignments. I took few assignments question from week 1 to week 11. Week 12 I not took because the solution is not out yet. It means that you still have the time to submit those assignment. That is week 12 assignment. Along with that, I choose few questions from the each week which I designed questions, like we have already discussed those things in the week 1 to week 12. Few of the questions we are going to discuss again. So all the important question that is favorable from the point of view of the exam, we are going to discuss it today. So let's start. Let's see the list of the content that has been covered in the entire week, and they are as follow. In week 1 we started with the crystallography. We discussed about the lattice, motive, point group, space group with very little. So we discussed more or less about the basics of the crystallography. Then after that we went to the structure of solids, where we discussed that sodium NaCl or 7 crystal system, 14 Bravell lattice, CSCl. Those kinds of structure we have discussed. We discussed the defects in the crystalline solid, like point defect, line defect, 1 dimension, 2 dimension, and 3D defect we have saw. We also saw the significance of the defects like dislocation in the screws, screw dislocation, edge dislocation. Then we went to the phase diagram. We discussed in detail about the ferrite and cementite, like iron carbon diagram. Then we went to the diffusion part, then phase transformation, which is governed by the diffusion itself, and then after that we went to the mechanical behavior of the material, where we discuss about the tensile strength, tensile test, and creep test, fatigue test, and Griffith criteria. The majority one that, like the most important one, is a Griffith criteria which we have studied. So in this particular entire course, we went through this list of the content. If you have any doubt in this particular content throughout the course, please let me know. If not, let's move ahead to the questions. We'll start with the question number 1. The aim of this particular session is to brush up all the concepts that we have learned in this week 12. So question number 1 is that which of the following lattice does not have threefold symmetry? Threefold, that is n equal to 3. And we know that if we have to rotate by, for the n fold, we have to rotate by 360 divided by n. Well, if we are talking about the threefold, it means that 360 divided by 3, which is nothing but 120. So if anything, like now we are talking about the symmetry. Let's take this particular triangle. Like intersection of the 3 lines. Here we can see it's 120. All of them are equal. So if I rotate line 1, line 2, line 3 in this anti-clockwise direction, what I will get after 120-degree rotation, 1 will coincide with the 2, and 2 will coincide with 3, and 3 will coincide with 1, and they will exactly form the same structure. So they are symmetry equivalent. So in the cube, we know that along 1, 1, 1, it's there. In this particular direction, symmetry is there, 120. Hexagonal also it's there. Like if we talk about the hexagon, Hexagon has, if about this particular point, if I rotate by 120, this point will coincide with this point, and so on and so forth, it will rotate. Hexagon also have 6-fold. If something is having 6-fold, they will inherently will have 3-fold in them. Trigonal also, it's having along the one of the axis. Okay, it's like we took a cube and we stretch it along one of the direction along 111, and so along 111 that 120 degree of rotation, the 3-4 will be preserved, while the orthorhombic is having the 3 2-folds, or to be more precise, 3 perpendicular 2-folds. So only this one is not having the 3-fold symmetry. So our correct answer is option B. Right. So let's if any doubt, let me know. If not, let's move to the next question, question number 2. So now here, the list of the crystal system is given to us in the column A. In the column B, their characteristic symmetry is given to us. Let's start with the cube. For the cube, what is the characteristic symmetry? We know that it's a 3-fold. That is 4-3-4 also, right? 4-3-4. So that it is going to match with the option C. Hexagonal, we know that it is having the 1-6-fold. So 1-6-fold. It is 1-6-fold, yeah. So it's going to match with B. Tetragonal is the one which is having the 1-4-fold. So here we can see that the option E is the right answer. Monoclinic. What monoclinic is having? It is having the single 2-fold. And triclinic, it's not having any symmetry, no spatial symmetry we can see. A trivial symmetry, it will always have that is 1-fold, and which is again considered as a no spatial symmetry. So with that, we have solved this question. Let's move ahead to the next question, question number 3. Now here we have to identify the direction that lie in 112 bar plane. There is a plane. In this plane, a multiple direction can lie. There can be a direction which is perpendicular to the plane also. So it is not lying in the plane. While we have to find the direction that will lie in the plane. And for that we know that we can use Weismann law. Let us say U, V and W is the direction which is lying in the plane HKL. So Weismann law say that if this criteria is satisfied, that is if this direction has to lie in this particular plane, then it has to satisfy U into H plus V into K plus W into L should be equal to 0. If this is satisfied, then it's going to lie. If not, then it won't lie. Let's see for the question number 1. So let's see for the first option. This is UVW and this is HKL. So 1 multiplied by 1 plus 1 multiplied by 1 again plus 1 multiplied by 2 bar, that is minus of 2. So what is going to be 1 plus 1 minus 2, which is 0. So first one is going to lie in the plane. Let's see about the second one. Since the dot product is 0, it's going to lie in the plane according to the Weismann. Now for the second one, let's try to do that. 1 multiplied by 1, 1, 1. Plus 1 multiplied by 2. It's going to be 1 plus 1 plus 2, which is 4. So it's not 0, so it's not going to lie in the plane. Let's see about the second one. So let's see about the third one. 1 multiplied by 1, 1, 1, 1, sorry, minus 1 times 1 plus 0 times 2 bar, that is minus of 2. So it's 1 minus 1 plus 0, which is 0. So again, third one is going to lie in the plane. Let's see about the fourth one. So in this way we can do all of them. Again, it's not going to lie, it's not 0. So overall, our only answer is option A and option C. So these two are going to be lie in the plane. Okay, so with that we have solved this question, question number 3. Let's move ahead to the question number 4. The question number 4 is very simple, but it's very important also. Like mostly people forget this. More or less what we have to do, we have to find that these things is used for which one. So a box a box bracket is going to use for the single direction. It's not the family of direction, it's a single direction. While this bracket is will use for the family of direction. This bracket, round bracket, is going to be used for the single plane, and this one is going to use for the family of plane. Right? So we must remember these things. Without this, it will be very confusing for us to solve any question, especially for the gate questions. One cannot solve them if they are not aware. Sometimes people think that okay, this is a plane or this is a direction. Some, there might be some confusion if we not remember this stuff. Let's move ahead to the question number 5. Now this question I took from the assignment. But question is telling that which of the following projection, there are the projection given to us, represent the diamond cubic structure. Both open and the shaded circle are the atom of the same kind, so we should not consider them to be the different. This black and this white one, both are the same atom. Next to them, showing the height from the projected plane as fraction of the unit cell. Okay, these fractions are representing the height. So what we know that in the diamond cubic, they are talking about the diamond cubic. Diamond cubic is a FCC, right, with a motif of OOO plus one more position is there, that is, sorry, we should not write in the curly bracket, OOO and 1 by 4, 1 by 4, 1 by 4. So it consists of the FCC lattice with the two motif. So if I draw one cube, here I can place my atoms, FCC atoms, carbon atom again. Now, from considering this to be this OOO, again after 1 by 4 there will be 1 by 4, 1 by 4, 1 by 4, will get one atom. If we keep on doing, like considering this to be the OOO and moving in the direction where 1 by 4, 1 by 4, 1 by 4 will lie. If we keep on doing for all the points, what we will get? We'll get that in front of this particular points, in front of this there will be the 3 by 4. This 3 by 4. About this. About this. Okay, sorry, about in front of this and in front of this, not this one. So if I see about this particular plane, if I draw this plane, what will I get? At the corners there are the atoms. At the face center there are the atoms, so we'll represent them like this. The corner we don't represent, like okay, 0 0 0 we can write, also 1 1 1 1 can write. While this one is 1 by 2, it is at the height of 1 by 2. This particular atom is at the height of 1 by 2. Again, here also there will be atom which is at the height of 1 by 2. and 1 by 2. Also, this particular center atoms are their face centered atom. This is also we have to go into, right? This is nothing but again 0. Now, these two atoms, in front of these two atoms, there will be the carbon atom, which is located at the height of 1 by 4. And then in front of this two atom, that is in front of this two atom, we can say that there will be the carbon atom, which is like from here, from the top it is 1 by 4, so from the bottom the overall height will be the 3 by 4. It will be the 3 by 4, and again it will be the 3 by 4. This position can be reversed, like one can say that no, 3 by 4 instead of 3 by 4, let's write 1 by 4, and here we can write 3 by 4. It's more or less everything remains same. So if we see like that, so we got that 1 by 4, 1 by 4, two atoms will be in front of these two, and two will be in front of these two. Okay, so P is the right answer. Here they are telling 3 by 4 and 3 by 4 will lie side by side, which is not the correct. Like they are telling all 3 by 4 are lying at the one plane, at the one height. All the carbon atoms, no. 3 by 4, 3 by 4, 1 by 4, 1 by 4. It's not. See, they are opposite. 1 by 4 and 1 by 4, they are opposite to each other. 3 by 4, they are opposite to each other. They are not like this. Okay. Same here. This is right. 3 by 4, 3 by 4, 1 by 4, 1 by 4. So right answer is P and R. So with that, we have solved this question number 5. If any doubt, let me know. If not, let's move ahead to the question number 6. So here, we have to do match the following. So a particular different voids are given to us, and their correspondingly critical radius we have to find. Okay, if we are having the triangular, what is a void over here which can be taken place? Sorry, I should not have drawn this like this. I should draw it like, okay. So here, this atom, this particular void size. So we know that for the triangular it is 0.115, for tetrahedral is 0.225, octahedral is 0.314, and the cubic is greater than 0.732. Okay. Let's move ahead to the question number 7. So this is a question. The enthalpy of formation of the vacancy in aluminium is 67.54. So delta HF is given to us. 67.54 kilojoule per mole. At what temperature the vacancy? At what temperature would the vacancy concentration become double then at the 0 degree Celsius? So we have to find the temperature. The temperature is missing at which, let's say, initially the temperature T1, which is at the 0 degree Celsius, that is 273 Kelvin. Here the vacancy concentration is N1. For the T2, the temperature we don't know, later the vacancy concentration is N2. So what is given to us? N2 is 2 times of N1. This is what is given to us. So now we know they are talking about the vacancy concentration, and we know the formula how we can calculate that. That vacancy concentration is given by small n over capital N divided by exponents is equal to the exponential of minus of n for enthalpy formation of the vacancy divided by RT. So we can put it over here. What we will get? This N2 divided by capital N. So the N2 will be, N2 I can write it as capital N times exponential minus of delta HF, which is going to remain same, divided by R times T, which will be equal to the 2 times of N1. N1 is capital N times, again I can write the same formula, exponential of minus of delta H divided by RT. I forgot to write exponential over here. So now let's do it properly and got cancelled. What we can say that again this temperature is 0 degree Celsius. Let's substitute all the values now. So what we will get from here is that exponential of minus of enthalpy of formation is given to us, that is 67.54 kilojoule. I will write 1000. R I can write 8.314 multiplied by T, which is missing to us, 2 times exponential of minus again 67.54 multiplied by 1000, the whole divided by 8.314 multiplied by temperature 273. So now all we need to do is we have to solve this equation. Okay, so let's try to solve this RHS first. What we will get is 2 multiplied by, we are going to solve this one first, exponential of minus 67.54 multiplied by 1000 divided by 8.314 multiplied by 273. So what we are getting is 2.36 2.386 into 10 to the power of minus of 30. This is what we are getting. Now we have to take the exponential of, so exponential of minus of 67.54 multiplied by 1000 divided by 8.314 multiplied by t. So if we can take, I can take log on both the side. Okay, I will take ln on both the side. What I will get, let's save this value in the a. Now what I will do, I will take the ln of a. I'll see what the answer I am going to get. So this ln, so what we are getting is minus 67.54 multiplied by 1000 divided by 8.314 multiplied by t. The value is minus of 29.06. So now from here I can find the t value. I can replace the position. This is going to be the plus now. So again let me store this in the v. What I will do is 67.54 multiplied by 1000, the whole divided by 8.314 multiplied by 29.06. So what I am getting, the value of the temperature is 279.54. Again the unit will be again Kelvin, right? Because we substituted the value over here in the Kelvin. Whenever we are solving the vacancies, this vacancy concentration equation, we are only going to deal with the Kelvin, not the degree Celsius. So now if someone wants the value in the degree Celsius, what they can do is they will subtract 273. So the final answer which we are getting is the temperature is 6.54 degrees Celsius. So let's see now. If we increase the temperature from 0 degree to 6, like we can almost say that okay 7, around 6.5 degrees Celsius, the vacancy concentration is going to be doubled, right? It's very interesting question. So with that we have solved this question number 7. Let's move ahead to the question number 8. In a binary alloy, the number of phases present in equilibrium at the eutectic point and that at the eutectoid point is number of phases. In a binary, first of all, we are talking about, you can take any binary alloy. Let's talk about the eutectic. Here, let's say it's a liquid. This is alpha, beta, liquid plus alpha, liquid plus beta, and alpha plus beta. What we are talking about is the eutectic point. This point, this is a eutectic point, where reaction is taking place, where alpha is liquid is converting to the alpha plus beta. So what and all the phases are present at this particular point? This is liquid is present, alpha is present, and beta is present. So total of 3 phases are present over here. Similarly, for the eutectide also, instead of liquid, it will just replace with the solid. Alpha is going to be beta plus gamma, or anything you can say. Any two solids it's going to be. So in this case, the number of phases present will be 3. So in the both the cases, at the eutectic point or at the eutectoid point, the number of phases are equal to the 3. Let's move to the question number 9. Okay. Oh, it's a good question I took from the assignment itself. Find the phase fraction of the alpha ferrite in a plain carbon steel with zero point 0.1 weight percent carbon at the temperature just above 7 to 7 degrees Celsius eutectoid temperature. Take the eutectoid composition of the steel to be this. So again, we are talking about the eutectoid. So let's draw it first, and then we'll try to understand the question again. So we have so what and all are given to us right now. So this is austenite, this is ferrite and cementite, alpha ferrite you can say. And this is again the alpha ferrite. Find the phase fraction of alpha ferrite. We have to find the phase fraction of the alpha ferrite. In a plain carbon steel with a zero point 0.1 weight percent at temperature just above. So, okay, so the steel which is having is given to us, it's a 0.1 weight percent. So the carbon percent is given to us. The temperature is just above the eutectoid, that is 727. So we are dealing somewhere around this particular temperature, just above the eutectoid, just above the eutectoid temperature. Take the eutectoid composition of the steel to be the 0.8. See, we know this composition, we know this composition. What and we already know that this composition from the page diagram is 0.02, right? What we have to find, we have to find the fraction of the alpha phase. How we can find the fraction of the alpha phase? We will use the lever rule. We will use the opposite lever arm. So we can find it that, okay, it will be given by 0.8 minus 0.1 divided by entire lever arm, that is 0.8 minus 0.0. If we want in percent, one can multiply by 100. So let's try to do this. 0.8 minus 0.1 divided by 0.8 minus 0.02 multiplied by 100. So what we got, that the answer is 89.74%. Okay, so with that we have solved this question number 9. Let's move ahead to the question number 10. If the activation energy for diffusion, okay, is this, at what temperature will the depth of diffusion be 10 times then 10 times that at the 25. See, in this questions we can assume that the composition which we are talking is the same. So in that case we know that the depth of diffusion is directly proportional to the root over dt. Okay. Now d, we know that d is equal to the d naught exponential minus of q over rt. So what is this? 70 kilojoule per mole is given to us. It's a q value, activation energy. At what temperature will the depth of diffusion be 10 times than that at the 25? Let's say that now we are having the case 1 where the temperature is 25 degrees Celsius, that is we can write 298 Kelvin. Here the depth of diffusion is x. Now the second case where the temperature we don't know, we want to find, which correspond to the depth of 10x. Okay. For both the cases we can apply this particular formula, x initial divided by x final, which will be equal to a root over d1 t1 divided by root over d2 t2 for the same diffusion time. So the t1 is equal to the t2. They are going to be cancelled out. So now what we are left, let's substitute all the values. So xi we took that it will be the initial is x, the final is 10x, which is equal to the root over d1 divided by root over d2. In d1 and d2 also we know that it only depend upon the temperature and the activation energy. So let's try to write that. So we can write both of them in one big bracket. The above I am going to write about the d1. d1 is d naught exponential minus of q, that is 70 multiplied by 1000, the whole divided by r 8.314 multiplied by T is a temperature, that is 298. Second case, again d naught exponential. Again we'll write the same thing, minus of 70 multiplied by 1000, 8.314 multiplied by the T. This is how we are going to solve. So let's try to do this. D naught and D naught is going to be cancelled. What we've got from here is 1 upon x, sorry 1 upon 10, which is equal to the root over exponential of, we can subtract these two values because they are in the same exponential type. So minus of 70,000 divided by 8.314 multiplied by 1 upon 298 minus of 1 upon 2. We can square both the side. So what we will get from here is that 100 which is equal to the exponential of, okay, I think let's not solve it very further. Let's go to the question number 11, which is as follows. We have to calculate the number of atoms in the critical nucleus. Number of atoms we have to calculate in the critical nucleus when solid copper formed by homogeneous nucleation at the temperature. So temperature is given as what temperature it is forming, 1002 degrees Celsius, using the following data. So we have, okay, so the data is given to us. The melting point of copper is 1083 degrees Celsius. Enthalpy of formation of nuclei is 1628 into 10 to the power of 6 joule per meter cube. The surface energy is given to us is 177 multiplied 10 to the power of minus 3 joule per meter square. And then the lattice parameter is given to us of the copper is 3.615 into 10 to the power of minus of 10 meter. So we have to find the number of atom in the critical nucleus. Let's first try to find the nucleus, the radius of the nucleus. The radius of the nucleus, we know it's given by minus of 2 gamma melting point of copper divided by delta Hm times delta T. Where delta T, we know that delta T is given by T minus Tm, which is the extent of undercooling. This again I took from the assignment. This question I took from the assignment. It's a very beautiful question. It's a minus of 2 multiplied by the gamma. The value of gamma is 177 multiplied 10 to the power of minus 3. All the units are joule per meter, and everything is in the meter and all. So we don't have to worry about the unit. Multiplied by the melting point of copper, that is 1022. Sorry, 1002. It's in the degree Celsius, so I will convert to the Kelvin, plus 273. The whole divided by delta Hm. Delta Hm is given, like enthalpy of formation is given by 1628 multiplied 10 to the power of 6, and we have to then again multiply it with the difference in the temperature, that is T minus Tm. T minus Tm. Okay, here I should write the melting point, that I made a mistake. 8 3. So now I have to write the difference, 1002 minus 1083. Since I don't have to convert them into the Kelvin, because anywhere 273 and 273 from this side will be cancelled out. So let's just try to find the answer of this particular thing. What the radius we are going to take? Minus of 2 multiplied by 177 multiplied 10 to the power of minus 3. Here we have to be very careful because lot of numbers are involved. 1083 minus, sorry, plus 273 divided by 1628 multiplied 10 to the power of 6 multiplied by 1002 minus 108. So this radius we have got, that is r is equal to the 3.64 into 10 to the power of minus of 9. Again the unit, see, we were only dealing with the meter and r is the distance only, so we can write it to be the meter. So this is the radius of nucleus we have got. So in this particular radius of the nucleus, let's say there will be the multiple unit cell will be there, right? So each unit cell will have some volume associated with this. So let us say there is a volume of one unit cell is AQ. The lattice parameter is given to us. We will multiply this with the number of unit cell, that is n. Number of unit cell multiplied by the AQ. So now this is the overall. We don't know how many unit cells are there. Let's try to find this. So now this volume should be equal to the volume of this particular nuclei, that is 4 by 3 pi r cube. In this, A we know, R we know, we just found out. So from here we can find the number of unit cell. Let's try to do that. It will be 4 over 3 pi r cube divided by a cube. Let's try to do this. This is the value of the r which we have got. Let me store this value in A. So now what I will do, 4 divided by 3 multiplied by pi multiplied by, recall, a cube multiplied by r multiplied by the lattice parameter a cube. So r cube divided by a cube. So now a is given to us, that is 3.615 multiplied 10 to the power of minus 10. a cube is, right? So we will make a cube of it. So from here we got that this value is given to be the 4276.95. So this is the number of unit cell that is present. What we have to find is the number of atoms, right? So we know the copper is FCC. So in one unit cell there will be a total of the 4 atoms, right? So now these 4 atoms and number of unit cell is given to us this. So all we have to do, we have to find the number of atom. What we will do, we will multiply 4 with the number of unit cell. So let's multiply this. So what we've got, the final answer to be the 17107. This many number of atoms are there. Last digit is 8, so let's round off to the 8. It was very beautiful question. Like we first found the number of, like the radius of the nuclei, then from that we found the number of unit cell, and from that we found the number of atoms. Let's move to the next question, question number 12. Okay, well, there is some misprinting in the question number. Let's so this is question number 12. The question says that the stage of annealing in which the free stream green from the green which high dislocation density. What is that? Which is that state? So you can know that, like, from the high dislocation density, getting the stream free green, like the new green, is a process of recrystallization. In the case of recovery, we covered that, okay, the annihilation of the point defects. Recrystallization is a process where the new grain form. Grain growth is nothing but the farm grain will grow. Okay. So with that we have solved this question, question number 12. Now this is a question number 13. So here, which solute will would cause the most significant hardening in the copper? So this is a copper. So we are replacing the copper with the this particular list of the atoms. So which one will cause more significant hardening? So that will be done by the one which is having the new metal which we are putting, the radius of that and the radius of the copper. The magnitude difference is more. Wherever we get maximum magnitude difference, that one will be the one which will cause the more hardening. Okay. And here we know that here let's find the difference over here. It's a 0.04. Here it will be the 0.05. It will be the what we can say 0.14. Here it will be the 0.30. The maximum magnitude difference which we have got is in the option D. So with that we can say that if we substitute copper with this particular atom, this particular metal, we are going to get maximum hardening in the copper. Okay, so let's move ahead to the next question, question number 14. So here we can what is asking that if the melting point of the polyethylene is this, so the melting point is given to us 140 degrees Celsius. It will not creep at, so at what temperature it, this is a list of the temperature, like at what temperature it's not going to creep. We know that when something get creep, if the test temperature divided by the melting temperature of that particular material, if it is greater than 0.5, then it is going to creep. So the opposite we can say that if it is less than 0.5, it's not going to creep, no creep. So let's work on this. So the melting point is given to us, so the T divided by melting point, that is 140 degree Celsius. If we want to convert this to Kelvin, so what I can write, I will add 273 to it. It should be less than 0.5. So the T should be less than 140 plus 273 multiplied by 0.5. Let's try to do this. So T which we have got is 206.5. This is again in the Kelvin, while the thing which is given to us over here is in the degree Celsius. Let's convert this back. So answer which we have got will subtract 273 from that. So what we got is that if the temperature is less than 66.5 degrees Celsius, then it's not going to creep. Right. So, so it is not going to creep at it will creep at room temperature. It will creep at 0 degrees Celsius. It will creep at 60 degrees Celsius also, but it's not going to creep at 196 degrees Celsius. Right. So with that we have solved this question number 14, and with that, yeah, I don't have any other question for today. So with that we have solved all the questions which are designed for today, this particular week, and let's have a look on to them. So we took variety of the questions from all the week, from week 1 to week 12. Let's have a look on to them. So this numerical which we solved today, it's more likely to come in the in upcoming exam, and also this type of questions are mostly favorable in the gate exam. It's more likely that they will come in the gate exam also. So with that, we conclude this particular session, and it was a great pleasure for me to be the part of this particular course, to be the TA of this particular course. And with this, I would like to tell you that if you have any questions, you can let me know. If right now you don't have, you can also put it on the discussion forum. You can also comment on this particular video. You can let me know. I will definitely respond to this. Also, I would like to say you that all the best for your upcoming exam. I hope you will score very good marks. Okay, guys, this was our last discussion, and with that, we have concluded our today's talk. Okay, bye bye. All the best.